The reason for suddenly bringing in the greatest integer function in a chapter on number-theoretic functions is this theorem. So it starts as we started many other results before by considering two number-theoretic functions small f and capital F such that they are related by this equation. For any positive integer n, capital F of n is the sum of the small f values of all the positive divisors d of n. If so, then for any positive integer capital N, say you consider the sum of the capital F values of all the positive integers starting at 1 and ending at this capital N, then this equals this other sum, where also n varies from 1 to capital N, but here we have the small f function, f of n times. So you see that here we need the greatest integer function times the greatest integer value of the ratio capital N divided by small n. The proof of this result is available in the book. I want you to go through the proof, and if you do not understand anything, please write in the comment section below. But more important for us than the proof of this result are the two corollaries that this one has. So let's see them. And this is corollary 1. For any positive integer capital N, the sum of the tau values of all the positive integers starting at 1 and ending at capital N is this sum. So you can see that this is just like this sum, except for f of n, here we have 1. And it's a one-line proof of this corollary once you recall what the function tau of n is. And this is the proof. You just recall that tau of n is the sum of that many ones as many positive divisors n has. So that means from this equation you see that you can think of tau as capital F in that theorem and the constant function 1 as small f, both of which are number-theoretic functions. And then you apply the above theorem. Above theorem is that theorem, and that just directly gives you this, that's it. And similarly we have corollary 2. Corollary 1 was about the function tau, corollary 2 is about the function sigma. Again, a similar thing. For any positive integer n, the sum of the first capital N sigma values of the positive integers, of course, equals this sum, where this time we do not have this place empty, instead we have n along with this greatest integer value. And here also the proof is just, you immediately get the proof by recalling what sigma of n is. Sigma of n is the sum of the positive divisors of n. So think of sigma as capital F in our theorem and the identity function as small f in our theorem, and then the theorem directly gives you this. Now let us see these two equations, this one and the previous one, in one example. Next we have example 6.3, where say we take this value of capital N 6. Then for this value, this tau series, tau sum, you can calculate, and I leave this to you to see that this is actually equal to 14. So you just put the values of n, calculate the tau values and take their sum. It should be 14. On the other hand, we also have this sum, where the general term is the greatest integer value of 6 divided by n, and in the sum n varies from 1 to 6, which of course is this sum. Now let's see the calculation. 6 divided by 1 is 6, and the greatest integer value of 6 is 6 itself, because the input itself is an integer. 6 divided by 2 is 3, and its greatest integer value is 3. Similarly, this one is 2, not this one is 2. This one is 1 point something, 6 divided by 4. So the greatest integer less than or equal to that is 1. That is why you have 1 here. Similarly, this one is also 1. and this one anyway 6 divided by 6 is 1 itself, so its greatest integer value is 1. So the sum you can clearly see is 14, so it's matching. Next, let us also see how we have the equation for sigma in this same case. So here is the corresponding sum for the function sigma, and this time its value is 33. On the other hand, if we take the right hand side of that equation involving sigma from corollary 2, then this is the right hand side. This time we no longer have just the greatest integer values, but we have them multiplied by n. So that just gives us this sum, which turns out, I mean, you can just use these values: 1 times 6 plus 2 times 3 plus 3 times 2 plus 4 times 1 plus 5 times 1 plus 6 times 1. So how many 6's do we see here? 1, 2, 3, 4. That means 24 plus 9, 33. So they are matching.